So the three tests that we have right now to help us decide whether or not a series converges or diverges aren't enough. We're going to need a few more, and then a few more after that. So the first one that we'll use is the integral test. And I kind of alluded to that back here with our comments in section 11.2 about the harmonic series. Basically, under the right conditions, whatever happens with one series is going to happen with the integral. So if the associated integral diverges, then so does the series. If the series converges, then so does the integral, and vice versa. So those two things go together. Now the conditions that we need to be met are this. We have to have a continuous positive decreasing function for f. So those are your conditions. Then basically if one converges, then the other one converges. If one diverges, then the other one diverges. So it's kind of a nice way to decide if something converges or diverges. So we'll do a couple examples there. The other one that we're going to get, and to me it almost feels like an offshoot of the integral test, but we are going to list it separately, is a p-series test. So a p-series is something like this. If you have the sum of 1 over n to some power, then the p-series converges as long as p is greater than 1. It diverges if p is less than or equal to 1. Let's take a quick look at this for a special case. What would this look like if p equals 1? If p equals 1, then this series is what? It's your harmonic series, right? But because p is less than or equal to 1, in this case it's actually equal to 1, we know this diverges. So it's just kind of a special case of the p-series test. So that's kind of nice. It tells us what we expected about our harmonic series anyways. But let's take a look at example C or A, and then maybe we'll do B and or C as well. So example A. We got the sum from n equals 1 to infinity of n over n squared plus 5. Want to know if that converges. Well, if you apply the nth term test from the previous section, you'd have, essentially n over n squared. N squared is going to get big faster than n. Eventually these terms will go to 0, but the nth term test in that case would tell us nothing. It just says inconclusive because the limit is 0. So another thing you can notice is that, well, I've got an n squared in the denominator and in the numerator. That's kind of hinting at a u substitution for an integral test. Okay, so let's do that. This is a positive decreasing function. So all these terms are going to be positive. As you put in larger and larger values of n, this series is going to decrease. The question is, does it decrease fast enough to get close enough to 0 that it's actually going to converge? Well, let's find out. So we're going to test the integral from 1 to infinity of x over x squared plus 5 dx. You could use a different variable if you'd like. That's up to you. Now, we don't have a nice antiderivative at the ready for this, so we're going to change our function. Let's do a u substitution. What would you suggest u equal? Yeah, x squared plus 5. X squared plus 5 du is going to be 2x dx. So 1/2 du equals x dx. Nice thing about the x dx is that I've already got it in my integrand. Now there's a couple other things I should probably take care of. One of which is that this is an improper integral. Fortunately, we just learned about those things not too long ago. So I'll rewrite this as the limit. Let's see. I should probably have done this first. Limit as b approaches infinity of 1 over b x squared over, or excuse me, x over x squared plus 5 dx. I'll do my change of limits and such like that over here, which is going to equal the limit as b approaches infinity. I've got new limits of integration. I'm not going to put in exactly what those limits are because I want to eventually change back. This is in contrast to what I did earlier when we dealt with stuff like this, that is U substitutions. I'm just going to call it alpha and beta. Making my U substitution, that's going to give me a 1/2 du in the numerator and u in the denominator. That 1/2 is a constant. I can bring that all the way out in front. 1/2, the limit as b approaches infinity of the integral from alpha to beta of 1 over u du. All right, at least it looks a little neater. Can someone help me with the antiderivative there? Yes, thank you. The natural log. So this is going to be 1/2 the limit as b approaches infinity of alpha to beta of the ln of the absolute value of u. I don't really need the absolute value of u because this is going to be going towards infinity anyways, but you could be careful about that if you'd like. Let's substitute back into our original function. Come back with our original limits. Limit as b approaches infinity. Our original limits were from 1 to b. 1 to b of the ln of x squared plus 5. So it's going to equal 1/2 times the limit as b approaches infinity of the ln of b squared plus 5 minus the ln of 6. Whew. A lot of work there. What's that limit going to be? As b grows to infinity, b squared is going to get big fast. And even though you're taking the natural log of it, you're taking the natural log of something that's getting really, really, really big without end. What's going to happen to this limit? Yeah, it's going to become infinity. Essentially, you have infinity minus ln of 6. So that ln of 6 is really not going to do much compared to infinity. Ln of 6. So if you're getting infinity as part of your limit, what's going on with the summation here then? Yeah, therefore, have you guys seen this triple of dots before? Therefore. So therefore, the series diverges by the integral test. Nice. I want to take you back a step and look at this and try and guide your intuition. Because what I found and what you're going to need when you get to Taylor series at the end of this course is a little hunch as to what's going to go on with this. Now let's think about n squared plus 5. As you start putting in larger and larger numbers, 1,000, a million, a billion, a trillion, etc., is that plus 5 going to make a really big difference? No. So what if we were to ignore it? What if we were just say, you know, let's just kind of pretend that wasn't there. For large values of n over n squared plus 5 is approximately the same as n over n squared, right? There's not going to be a huge difference of that, especially if you're working with terms like a million squared is a trillion. If you had $1 trillion and someone said, hey, do me a favor for $5, are you really going to be all excited? Probably not. But 1 over n squared reduces, right? What's 1 over n squared? Or excuse me, n squared over n reduces to 1 over n. What do you know about the series made up of terms of 1 over n? There's your harmonic series again, right? So you can look at that and say, well, that's just like really close to a harmonic series. I expect that to diverge. And you'd be right. And we saw that with the integral test. But for me, it's always been very helpful to kind of have an idea of what to expect before I actually did those calculations. And I think it'll be helpful for you as well. Are we okay with example A? That was the integral test. Yep. Let's take a look at a different one. This one's going to be another substitution. What about this one? Let's see if we can't get some intuition about this one as convergence or divergence. What do you think is going to happen with that one? You can take out the 9. What about the n squared plus 4? Is that plus 4 going to do a whole lot for large values of n? So this is approximately the same as 9 over 1, which I didn't really need to write the 1, n equal 1 to infinity of 1 over n squared, right? What do you know about 1 over n squared? 1 over n times 1 over n, good. But is there anything else that might be relevant from something that we've just kind of covered? That looks like a p-series, right? P-series with p equal 2. If this is a p-series with p equal 2, is that going to converge or diverge? Alicia, what are you thinking there? Yeah, if p is greater than 1, then it's going to converge. So this is a convergent p-series with p equal 2. That's p-series. P equal 2. Nice. So you expect that to converge. Now on a test, I'm not generally going to ask for hunches. There are a few exceptions, but we will get there. This one, if you take a look at it, does have a kind of familiar form to it, and I don't think I want to take the time to do all that out just now, so let me just kind of show you what happens with that one. The antiderivative of that one is just simply the arctan of x over 2, and the arctan of x over 2, if you take the limits here, does end up to be something finite. Arctan of infinity is actually pi over 2. That's where the arctan converges as this approaches infinity. So because the integral is finite, the series converges. All is well and good with the world. All right, so our intuition matches there. You can actually finish showing this with the integral test. But not all of them are going to be quite that long. Some of them are going to be a little bit longer. Some are going to be a little easier. Let's turn our attention to this one down here. Could the integral test be used to determine the series, whether or not this series converges or diverges? Well, we've got 2 over the 5th root of n. If I wanted to use the integral test, I need to assure myself that it's a positive decreasing function. Suppose you could do that if you wanted to graph it. Probably be an easiest way to do that. So let's take a quick look at the graph. 2 over x raised to the 1/5. Let's change it up a little bit. 2 over x raised to the 1/5. And I want to look at that for positive values of x. There you go. So I think it's got everything we want. It's a positive valued function, so its graph lies above the x-axis. It's continuous and decreasing, so it's got everything that I want. I could use the integral test to show that this converges or diverges. But there's an easier way to do this one. It takes about 10 seconds. Does anyone spot it? Jesse, I think. P-series, yeah, absolutely. So this could be rewritten as the sum. I'll take the 2 out front. N equal 1 to infinity. 1 over n to the 1/5 power. All right. Does this converge or diverge? Diverges. Yeah, diverges. So it's a divergent P-series. P equals 1/5. Nice. How about down below? Does this one look like it would converge or diverge? What would you have to do to decide? What strikes your, what catches your attention here? How about if we rewrite it? How about if I rewrite it as 1? Can anyone think of a way to rewrite 4 or 9 or 16? Does anyone see anything? 2 squared, 3 squared, 4 squared. And in general, this series is a sum from n equals 1 to infinity of 1 over n squared. What do you think on this one? P-series, good. And what happens with it, Marlon? Good, convergent P-series. This one's actually amazing. One of my heroes mathematically is a guy by the name of Leonhard Euler. This was called, I think it's called the Basel problem. And he actually figured out what that adds up to. Now the fact that it adds up to anything, well, we know it converges, that's good. The fact that you're able to calculate it and it turns out to be pi squared over 6 is just the coolest summation. Wow, how does that work? How is that got pi? Remember what pi is? Pi is the ratio of the circumference of a circle to its diameter. Somehow that's wrapped up in this summation, pi squared over 6. Wow, just really, really cool. All right, let's keep going. Isn't that cool? No one else? I'm the only one?
Pi squared over 6 on the exam,
Pi,
do you get extra credit?
pi squared over 6. I think Stanley Keg on the exam would be. Yeah. All right. This one. There's another efficient way to do this one. Let's take a look at these terms. This is really the sum from I equals 1 to infinity of 1 over, well, you could write it as I times the square root of I, and that'd be fine. But you might be better off reflecting that square root of I is really I to what power? I to the 1/2. And now that I write it as I to the 1/2, I can combine these two things in the denominator and get the sum from I equals 1 to infinity of 1 over I to what power? 3/2. Anika, What do you think? Is this going to converge or diverge? Yeah, it converges. So this is a convergent. Why does it converge? Yeah, it's a p-series. P greater than 1. So convergent p-series. Nice. Nice. Let's see. Here's another gem from Leonhard Euler. This is called the zeta function. And it has a lot of implications for higher math, including it's the foundation of something called the millennial problem. If you want to get yourself a quick $1,000,000, you can solve one of the millennial problems regarding the zeta function. I don't have time to describe that now. But if you put in a 4 here, zeta of 4 equals pi to the 4th over 90. So kind of like our friend, the sum of the reciprocal of the squares, we got pi squared over 6. Similar kind of thing here, you get pi to the 4th over 90. I think he did it for even numbers up to about 12 maybe. In any case, he used that result, and you can use that result to figure out a couple of these other ones. So for instance, the sum from n equals 1 to infinity of 5 over n to the 4th power. Let's understand what's being done here, because there's a couple things that are pretty cutesy. First of all, you just raise everything to the 4th power, you drop the parentheses, you factor out the 625, and then you realize that, oh, this much of it here is this result up here. So you can replace that with the 625 and all is well and good. But let's take a look at this one. How come I can't immediately say, oh, well, that's just really, you know, the zeta function at 4 again? It's close, but it's not quite the same. Why is it different? Is there anything different about this and this? Let's take a look at the first few terms of this series. So the first few terms of that series are going to be 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th, and so on. But if you take a look at this series, where does it start? It starts at 5, but effectively it's this series starting at 3, right? So it's missing those first 2 terms. And if you play around with this, and you do a little change of variables here, you can start your series at 3 instead of starting this series at 5. Starting this series at 5 and this series at 3 give you the same thing. The only thing you're missing are these 2 terms. What you're missing is right here. So if you say, hey, I'll just treat this as if this is the sum of all of these things minus this part, that's where you get your answer. Is you're just adjusting the starting there and subtracting off of the terms that you're missing right there. So here's your final answer on that one. Okay, another nice gem from Leonhard Euler. He was prolific. If you were to accumulate all the stuff that he wrote during his lifetime, you'd have to have about 100 encyclopedia-sized volumes to add it all up. He was amazing. Oh, and he was blind the last 17 years of his life, too. Throw that in the mix. He kept on producing math.